The climate crisis is more than just an issue. It's a global emergency. And the drivers behind this emergency? It's us. Every year, human activity like generating power or manufacturing goods puts over 30 billion tons of carbon dioxide into the atmosphere. And this not only increases global warming, but also its detrimental consequences. There are many new innovative technologies being researched and developed to capture carbon dioxide emissions and use them. But in order for these technologies to be really impactful, they have to be targeted to industries that emit a lot of carbon dioxide and to produce valuable products. Industries like the alcoholic beverage industry, that production accounts for approximately 4% of all annual CO2 emissions. Or industries like the ethylene production industry, which produces millions of tons of carbon dioxide every year, but it also produces a valuable commodity used for so many consumer goods.
For our project, we've developed and optimized an electrocatalytic process to sustainably convert carbon dioxide emissions from the alcoholic beverage industry into ethylene. Our design integrates an electrolyzer and cryogenic separations to produce pure ethylene, offering a sustainable alternative to conventional ethylene production methods. This model was designed for integration at the tail end of a Tito's distillery plant located in Austin, Texas.
The electrolyzer is the heart of our process. At its core, it's a device that utilizes electrolysis to convert CO2, which is a fully oxidized low-energy form of carbon, into ethylene, a higher energy, more usable form of carbon. Electrolysis is essentially a process by which electricity is used to drive otherwise thermodynamically unfavorable reactions. At the center of the electrolyzer, there's an anion exchange membrane. On both sides of this, catalyst nanoparticles are deposited on conductive supports, making up the anode and the cathode. These layers are sandwiched by diffusive transport layers and flow fields. Across these various layers, there are multiple mechanisms simultaneously in motion. On the cathode side, humidified CO2 is fed into the electrolyzer. This CO2 then diffuses and adsorbs to reactive catalyst sites. Using electricity and water, which diffuses across the anion exchange membrane from the anode side, the electrolyzer reduces CO2 into ethylene, at which point it exits the cell. At the same time, hydroxide anions produced from this reaction diffuse across the anion exchange membrane towards the anode catalyst, where the oxygen molecules combine to produce oxygen and some water. Modeling these many mechanisms can be very difficult due to the need to combine multiple physical models. However, we can somewhat accurately model the conversion of CO2 using experimental data from literature. Using reported Faraday efficiencies, which are essentially the number of moles of product produced per number of moles expected to be produced based on the charge passed, we were able to model the molar flow rates of ethylene and any of the side products produced.
The output from our electrolyzer includes carbon monoxide, methane, propanol, oxygen, ethanol, acetic acid, and formic acid, with ethylene and oxygen as our major products. The electrolyzer's total power consumption was estimated at approximately 11 megawatts to achieve our desired output. Our group used COMSOL multiphysics software to model critical physical parameters within the electrolyzer. We analyzed temperature and pressure trends to predict internal changes occurring in the electrolyzer.
Ethylene is isolated through various separation processes. CO2 reduction reaction products exit the cathode at 866 moles per minute and 55 degrees Celsius in 4 bar. These products include ethylene, carbon monoxide, methane, hydrogen, propanol, ethanol, acetic acid, formic acid, and the remaining CO2. The high exit pressure is what pushes these products throughout the rest of the separations process. The stream is cooled to negative 25 degrees Celsius before entering a knockout drum. The knockout drum separates the gas and liquid products using gravity to force the entrained liquid down out of the gas. A demister ensures a liquid-free gas exits at the top of the vessel. The liquid products are sent to a tank and treated as waste. 783 moles per minute of gas products exit the drum. These products are cooled to negative 90 degrees Celsius and enter the first cryogenic distillation column. Cryogenic distillation works by cooling gases to liquids and using multiple stages to exploit the vapor-liquid equilibrium differences between fluids to separate them. In this column, hydrogen, methane, and the remaining CO2 are separated from ethylene and carbon monoxide. The second cryogenic distillation column separates ethylene and carbon monoxide, producing 564 moles per minute of 99.9% pure ethylene.
On the anode side of the electrolyzer, oxygen gas is produced in an aqueous solution. The solution goes through a knockout drum which separates the gaseous oxygen from the aqueous solution of water and electrolyte. After separating the two phases, the electrolyte solution is recycled to the electrolyzer and 99.9% pure oxygen is produced at 2,098 moles per minute. Based on current market sales prices, the ethylene and oxygen produced in the process is expected to generate $12.7 million in revenue. However, this revenue does not make this process profitable. With these projected sales, the process will be at a net loss of $4 million. Unfortunately, the reality of carbon reduction processes like ours is that they are rarely economically viable. And so we propose a few strategies to combat this. Firstly, on the production side, ethylene would have to be sold at a higher price of $1,890 per metric ton to break even with production costs. But outside of this, we believe that increased investments in research and development for carbon reduction technologies can help to increase scale while also bringing down costs. Additionally, governments can provide financial incentives, tax credits, grants, or subsidies to businesses and individuals to encourage them to invest in carbon reduction technologies.
The overall goal of this project has been to create ethylene that is carbon neutral or carbon negative. Due to the high energy dependence of the electrolyzer, the renewability of the energy source that we use dictates the overall sustainability of the project. With energy sourced from coal, the project is very carbon positive and would release 80 million kilograms of CO2 per year. However, utilizing wind energy, which is abundantly available in Texas, our process becomes very carbon negative and removes nearly 28 million kilograms of CO2 annually. When comparing our process to traditional ethylene production, our process removes 3 times as much CO2 as is produced by traditional methods.
Though our design can drastically reduce the CO2 emissions from vodka production, specifically the Tito's vodka plant in Austin, Texas, there are several recommendations that we have for this project. More research into the lifetime of the electrolyzers is required. Determining this, as well as the scalability of the electrolyzer, was difficult because most electrolyzers are only designed on laboratory scales. Several high-level assumptions were made when designing our electrolyzer, including the reaction occurring inside it. More advanced modeling is required to implement this process. Additionally, several assumptions were made for the separations processes. For instance, pressure drops were estimated across all unit ops, and the high outlet pressure of the electrolyzer was used as the force that pushed the fluids throughout the process. Thus, no compressors are used in this design. Cryogenic distillation was used as a convenient method to separate the gases, but more energy efficient or alternative methods such as adsorption could be explored. Overall, our process indicates that electrocatalytic conversion of CO2 emissions to ethylene at a vodka plant is feasible and carbon negative if the process uses renewable energy.